Hello everybody. In this particular chapter, we are going to see how ECU or HPC or SOC is developed for ADAS application. ECU stands for Electronic Control Unit, HPC stands for High Performance Computer, and SOC stands for System on Chip. Basically, all these three are the same. Basically, ECU, HPC and SOC are the same but only with various configurations. ECU, you can call it a mini computer. HPC, you can call it a very high performance computer with very high processing power, and SOC stands for even more higher processing computer, or it can even comprise of a system which has multiple ECUs within it. But basically all these three are mini computers which must be developed for ADAS, and we will see in step by step how these are developed for ADAS applications. Now, developing an electronic control unit on system on chip for advanced driver assistance is a complex multi-phase process involving hardware, software validation and integration with automotive OEMs. So, I hope you understand that developing electronic control unit is not just the role of the tier 1 or tier 2. It requires extensive collaboration with automotive OEMs. For example, if you are a tier 1 who is developing this, you require collaboration with OEM and also tier 2 and also tier 3, because a ECU comprises of both hardware, software, and you need to interact with some validation companies which specialize in validation. You need to collaborate with some companies which are simulation specific. So below is a detailed breakdown of development life cycle. Market and requirements definition. Identify ADAS use cases. First of all, you need to identify the various ADAS use cases for which the ECU is developed. Determine which ADAS functionality the ECU or the SOC will support. Are you going to support adaptive cruise control or lane keeping assist or automotive emergency braking or parking assist or blind spot detection or vehicle turn assist? All these use cases must be clearly identified, because based on this only the latency, the power and the efficiency are determined. So next comes the defined performance metrics, that is latency, power efficiency, safety levels and the computational power. Next comes gather OEM and regulatory requirements. OEM specific needs, customization for different car manufacturers. Okay, based on the OEM specific needs, you need to customize for different car manufacturers. Safety standards, ISO 26262, ISO 21434 and AEC-Q 100. These are the various safety standards that need to be adhered to. ISO 26262 is functional safety, 214314 is cyber security. Now, both are clearly explained in the concerned chapters. The regulatory compliance, UNECE, NHTSA, NCAP safety ratings. These are the various regulatory compliance that need to be complied by the ECU. Now, let's see the architecture and design, how we go about architecture and design. When we come to, I'm saying this in the perspective of OEM or tier 1 company. Suppose you are a tier 1 company, you will follow all these steps. First, you need to select a SOC. Choose between off-the-shelf SOC or custom SOC. There are many off-the-shelf SOCs like NVIDIA Drive, Qualcomm Snapdragon Ride, Mobileye IQ. All these are off-the-shelf system on chips. Or you can also customize the system of chips like Tesla self-driving chip. Alright, next comes the key components. What are the key components of the ECU? One is the CPU, GPU and TPU. For general and AI processing, CPU stands for central processing unit, GPU stands for graphical processing unit and TPU stands for telematic processing unit. Next comes the NPU, which is the acronym for neural processing unit, for deep learning, object detection and sensor fusion. When it comes to ISP, image signal processor, for camera data processing, this is very important for camera data processing, especially whenever the camera is live streaming. This processor is the one which actually extracts the meaning of the data. Now, coming to the memory and interfaces, well, various types of memories like LPD, DR5, PCLE, CAN-FD, Ethernet AVB, all these are comprising of memory and also the interfaces. Next comes the power and thermal management. optimized for automotive environment, minus 40 to 125 degrees centigrade. Now when it comes to software architecture, the real-time operating system on automotive OS are QNX and Linux based. Middleware, AI frameworks and OTA update capability for firmware updates. Now these are all the various software architectures and software algorithms that need to be developed. You need to develop a software for sensor fusion, for interfacing of communication stack, for AI frameworks like TensorFlow Lite or PyTorch, and also OTA update capability for firmware updates. In the chapter about OTA, I clearly mentioned about the various companies which are handling the OTA. OTA stands for over the air. Okay, again there is a separate chapter for over the air. When it comes to development and implementation, when it comes to hardware development, okay, the first step is the PCB design, which ensures or which must be ensured of high speed signal integrity, EMI EMC compliance. EMI electromagnetic interference and electromagnetic compatibility must be complied. Next comes the prototyping, FPGA based emulation before ASIC tape out. Okay, first it must be emulated based on this FPGA before the ASIC is rolled down. Next comes the manufacturing. When it comes to manufacturing, you have to outsource it to companies like Samsung or any other tier 1 companies for SOCs or tier 1 suppliers for ECU assembly. And when it comes to software development, again software what are all the various applications for you for development of software? It is sensor processing, camera, lidar, radar, data pipelines, and also perception algorithms, CNN for data object detection, YOLO and ResNet, and sensor fusion, which comprises of Kalman filters and Bayesian network, and control algorithms, PID for adaptive cruise and path planning. So this is how you go about development of hardware and also the software. Okay, we touched upon the hardware design, the software architecture, next the hardware development and also the software development. Let's proceed further. Now when it comes to verification and validation, validation comprises of simulation testing and software in loop, MATLAB, Simulink, Carla simulators. Next comes the hardware in loop, where rigs are provided by DSpace. NI stands for National Instrument Platforms. So there are some companies which are expert or which specialize in software in loop and hardware in loop. So if you are a tier 1 company, this simulation part you outsource to those companies, or if you have this facility in house, then you can do it in house also. Okay, this is totally the choice of the tier 1 company. Next comes the real world testing. Real world testing, closed course testing like controlled environments, fleet testing millions of miles in varying conditions, edge case validation, where you check the vehicle in rain, snow, glare scenarios. Now this real world testing, you usually do it in collaboration with the OEM. If you are a tier 1 company who is developing the ECU or SOC, you embed that SOC in a vehicle and do this real world testing in collaboration with the OEM. Along with the OEM, you take your car to some very remote places like Norway or Sweden, or you can go to some very hot places like Jaipur or Jodhpur, where temperatures can go up to 52 degrees centigrade. So depending upon your real world testing or real world testing scenario and requirements, along with the collaboration of the OEM, as a tier 1 company, you take the vehicle to the required place. Now coming to the safety and cyber security, again you have to verify and validate that this compliance is properly met or fulfilled. Okay, and you do it by failure mode analysis and fault tree analysis. There is one more testing called penetration testing. I clearly explained this in the various types of testing that happen on the ECU. So this penetration testing also must be succeeded. It must be the successful in this penetration testing. Okay, now coming to the certification of production, the first certification step is automotive qualification. Okay, this AEC Q100 grade 21 for temperature and reliability, and IATF 16949 for quality management for automotive. This is a very popular standard, especially used for quality management. Now when it comes to OEM integration, the vehicle level testing, which can also be combined with the real world testing. Okay, this vehicle testing can be sometimes combined with real world testing, and also the calibration, fine tuning for specific car models. This fine tuning is nothing but modifying the vehicle or the ECU for different variants. For example, let me give you a small example. Mercedes has various variants. It can be a sedan or a SVU, and within sedan also there is a C class, S class. So once you prepare a ECU for Mercedes, you have to fine tune differently for C class and fine tune differently for S class. And just give me a crude example. And when it comes to mass production, how do you ensure that ECU is mass produced? With the help of tier 1 suppliers like Bosch, Conti, ZF, they are the one who finally produce the ECU. Actually, it is the onus or responsibility of these companies to produce the entire ECU. Usually, the companies which produce the prototype ECU, they only mass produce. It is in very rare cases that ECU is prototype is developed by one company and it is mass produced by other company. It is very rare case. Usually, I repeat, prototype ECU and the mass production ECU are done by the same company. Okay, next comes the supply chain. Okay, as a tier 1 company, it is your responsibility to ensure that all the various ingredients or the components or the subsystems of the ECU are available in the market. So it is your responsibility to ensure a proper supply chain, a proper logistical structure. Now, when it comes to deployment and post-launch support, now first is after the deployment, the most important is OTA updates, over the air updates. So once even after the ECU or SOC is fixed inside the vehicle, you can continuously improve the algorithms and fix bugs with the help of OTAs. Okay, by data transfer or patches transfer, you can always improve the algorithms with the help of OTA. And next comes the field monitoring. Collect real world data for future enhancements. Okay, now collecting the real world data for future enhancements, recall management if needed, address safety critical issues via updates or replacements. Okay, now this recall management is one of the important how to say reasons why OTA was developed in the first place. So with the help of recall management, you address the safety critical issues through updates or replacements. So sometimes usually OTA can take care of the recall management, but sometimes if the vehicle must be recalled to the dealership or service, there's no choice but to recall the dealership and then do a replacement. Now what are the key challenges? Key challenges is first is the functional safety, next is real-time performance. Well, as I said, this latency is something which must be taken care, and also the power efficiency, cyber security, and cost optimization. Okay, so these are the various key challenges. Balancing performance and the bill of material cost. You can prepare a very high processing ECU, but the cost must also be viable. Okay, also when it comes to business, cost viability is a very important parameter. Now let's see as an example ADAS SOC development flow. First is you identify the requirements, and what are the activities? You define ASIL level, OEM needs, and NCAP goals. Next is the design. You select the SOC, whether it is NVIDIA or Infineon or or Texas Instruments. You need to select the off-the-shelf or a customized SOC, and then you design the PCB layout, and also you do the AUTOSAR configuration. Now I already said AUTOSAR configuration is a very complicated activity which requires tools like Vamsi configurator. The Vamsi configurator is both complicated and also expensive, which requires very specialized expertise. Now after designing comes the development. Well, development includes AI model training, sensor fusion algorithm. These are the steps involved in the development. After development, you test, and this hill, SIL, all the in-loop testing which I have covered extensively in the concerned chapter, this comprise of the testing. Next comes certification, and when it comes to certification, this ISO 26262, UNECE, AEQ Q100, all these various certifications are required. Last but not the least, when it comes to production, it is tier 1 manufacturing. As I said, it is always the tier 1 which takes care of the production of the ECU. Now to continue further, now what are the key challenges? What are the key challenges in developing the ADAS ECU. Let's see them in a very elaborate manner. Now the sensor limitations and environmental constraints. Weather and lighting conditions. Whether sensors struggle in low light, rain or fog, reducing object detection accuracy. For example, forward collisions may fail at high speeds or adverse weather conditions. Next is, in automotive conditions, signal to noise ratio is a very important parameter. So distinguishing critical signals from environmental noise remains difficult, especially in moving objects. Next comes the sensor fusion complexity, and combining data from multiple sensors requires high bandwidth communication and advanced algorithms to avoid network overloads. Okay, so addressing the sensor limitations in the various environment constraints is the biggest challenge as far as developing the ECU is concerned. And when it comes to computation and hardware demands, even though modern ECUs are capable of handling some high processing power, growing of the processing power on par with the ADAS requirements is a big challenge. There are some very high processing power ECUs, no doubt about it, but the ADAS requirements are also growing drastically, and processing power keeping up with the ADAS requirements is the biggest challenge. Modern ADAS ECUs need multi-core architectures, for example chiplets like Boss's Eagle M, to handle AI workloads. Okay, example 250 TOPS for perception algorithms. However, balancing performance with power efficiency is critical. So even if there is a ECU which can handle that high processing power, power supply to that particular ECU can also be critical, and also it is challenging. And when it comes to thermal and ECU management, high performance processors generate heat, requiring robust thermal designs and electromagnetic compatibility solutions to prevent interface. Now this is very important. Okay, not just in ADAS ECU, in any ECU. I am sure everybody seen in some WhatsApp videos or Facebook videos that some scooters or cars are catching fire during charging. That is nothing but failure in thermal and EMC management. When thermal and EMC management is failing, then that leads to automobile catching fire. And when it comes to scalability, modular designs are needed to adapt to varying autonomic levels, L2 to L4, and OEM specific requirements. Okay, so based on the OEM specific requirements, you have to ensure scalability is properly present. It should be properly scalable or expandable. Now when it comes to safety and regulatory compliance, this ISO 262 and ASIL standards, ASPICE and cyber security, legacy system and integration, all these particular standards must be met. ECUs must meet stringent functional security. For example, within ADAS, in the ADAS ECU, various functionalities have various ASIL level. For example, for something like automatic emergency braking, ASIL D is important. For something like lane departure warning, ASIL B it is only ASIL B level. So through the failure modes and effects analysis and fault injection testing, ECUs must be ensured of meeting these functional safety requirements. And of course, ASPICE and cyber security, achieving ASPICE level 2 and level 3. Now I also explained in the system engineering how you can achieve ASPICE level 2 and level 3 maturity for software processors, and complying with ISO 21434 for cyber security add complexity. Okay, as I told in the, or rather as it is told in the ASPICE chapter, usually OEMs don't approach a particular tier 1 company unless it is ASPICE 2 or ASPICE 3 certified. Now what is this ASPICE, what is this certification? It is clearly explained in the relevant chapter. When it comes to legacy system integration, reusing software across ECU generations while ensuring compatibility is used. There are plenty of vehicles where still some old generation ECUs are used. So ensuring that these old generation ECUs or legacy ECUs are compatible with newer safety challenges, safety standards is very challenging. So old generation ECUs must meet with the new generation safety standards. That is the challenge. Now coming to the validation and testing complexities, real world scenario where billions of test miles are required to validate rare events, and that is where simulation tools struggle to replicate. Now, even though simulation tools are good or doing a good job, replicating every real world scenario is a big challenge. It just cannot replace the billions of test miles that can happen in the real world. Now, coming to the next closed loop developed gas, silo testing phases lack feedback loops, prolonging development lifeline. What is meant by silo testing phases? It means that component is tested separately, it is integrated separately, and vehicle level testing is happening separately. So when these component level testing and integration level testing and vehicle level testing are happening separately, it lacks the feedback loops, okay, and which this prolongs the development timelines. And recomputation and the simulation, validating AI driven decisions requires computing computing sensor data in simulated environments demanding high fidelity models. Okay, so this recomputation and simulation are extremely important and extremely challenging. It requires recomputing sensor data. This word is very important. Okay, so to validate AI driven decision, recomputing the sensor data in various environments, it demands a very high fidelity models. That means very highly dependable models which can be recomputed and simulated. Now, when it comes to data management and system integration, the magnitude of data almost improving AI accuracy from 98 to 99.9%, even increasing by 1.9%, it requires exponentially larger data sets necessitating scalable storage and processing infrastructure. Okay, whether you are storing the data in a cloud or within the ECU itself, how to say, exponential level of data sets or exponential level of data storage is required. And when it comes to interoperability, integrating diverse components while ensuring real-time performance adds layers of complexity. Okay, now coming to the power supply design, meeting noise standards and managing radiated emissions in compact ECU designs are persistent hurdle. Okay, so when it comes to automobile, there may be some radiated emissions which can interfere with the seamless working of the ECU. That's again an important hurdle that needs to be overcome. Last but not the least, cost and time to market pressures. Now, as OEMs are competing with each other, this cost and time to market pressures are more and more on the OEMs. So this requires high development costs, iterative testing, compliance efforts, and custom OEM integrations drive expenses. Okay, and coming to the balancing innovation and safety, rapid AI ML advancements must align with rigorous safety and often slowing deployment. So in short, what I am trying to say out of these two sentences is, on one side you need to market and release into the market as quickly as possible, but all these various types of testing must be done before you release. So balancing the testing time and also ensuring that you release into the market by being innovative and safe, is a very big challenge for the automakers. Now, what are the various emerging solutions? Now, every challenge has a solution. There are some solutions like chiplet architectures, which comprise of the modular designs, and they enable scalable performance and cost efficiency. Now, chip architecture is one thing, and chiplet architecture is, it's like a mini chip. So with the help of mini chip, you are able to develop multiple permutations and combinations of the architectures. And when it comes to unified ALM tools, platforms like ETA's deterministic middleware streamline ASPICE and IS4 262 compliance. Okay, so there are some platforms which are like off-the-shelf solutions for meeting ASPICE and IS4 262 compliance. And of course, next case, the contract-based design, formal methods and component level contracts, they improve the verification efficiency. Okay, so these are the various types of the emerging solutions. So based on the contract base, or you outsource the designing, and outsourcing company, they takes care of the formal methods and component level contracts, thereby improving the verification efficiency and efficacy. All right. Thank you. I know this video was slightly longer, and thank you for your patient listening.